Okay. So what I'm going to do today is I'm going to show you this very important equation that governs all simple harmonic motion today that we're going to cover. So when we talk about simple harmonic motion, we're talking about oscillation. Now let's take a look at two examples of oscillation, and then we're going to infer what's the general rule for anything that oscillates. So let's take a look at this case. Yeah? So if this object over here of mass m is attached to a spring, and this at this position over here, the spring is at its natural length. Now, what happens if I were to stretch it a little bit by distance x? Now, do you agree that the force, I think I mentioned this the last time, is actually equal to kx? K is the spring constant, it is the stiffness of the spring, and x is the eccentricity. But something is missing. Exactly, that must be minus, correct. So that's why I left the space for there. Now the reason why it's minus is because
direction.
Exactly, it's direction. So if your x is this direction, the force will be this direction. If your x is this direction, the force will be the other direction. Got it? So therefore this is equal to ma, and a is therefore equal to minus k upon m x.
So, but doesn't the key change as you do it for
K shouldn't change if you don't stretch it too much.
the spring?
If you stretch it beyond the limit of proportionality, then you change. Then you will plastic deformation. Yeah? Okay? So if you don't stretch it too much, it is linear. If you stretch it a lot, then you start to go the non-linear behavior. So now the other situation I'd like you to take a look at is a little bit less intuitive. It needs a little bit of more derivation, but you'll see that it actually arrives at something similar. So let's take a look. Mass m over here, you agree that the force acting on it is mg. So if the force acting on it is mg, I can actually resolve it into two components. This force and this force. Yeah. Now this force over here is the one responsible for accelerating it back. Agree? Now if I were to draw the mg over here, the force over here, the force over here, this will be theta. So therefore this force over here is mg, sorry. This force over here is mg sine theta. Mg sine theta, because this is the opposite hypotenuse. Cool? Is it okay? Can I still follow up? No, you're not land yet. So the restoring force is equals to mg sine theta, which is actually equals to mg. If I call this is part where some people will start to jump already. Can you see that sine theta is approximately equals to theta if the angle is small? Have you seen this before? Okay, if you don't believe me, you change your calculator to radians mode, and then you sine 1 degree equivalent to radians, and then you find that the value over here is the same as the 1 degree radians. It is a mathematical rule where sine theta is actually approximately equal to theta minus theta cubed over 3 factorial. So if the angle is small, this factor over here goes to 0. Therefore, this is actually equals to mg x upon L. Now we need to put a negative sign over here. Why? Because if we measure x, actually x should be measured from here to here. Therefore, the force is actually in the negative direction. Now this is the part. This is equals to ma, which you can strike it off. A is actually equals to minus g upon L x. Now what do you notice about this form and this form? There are two similarities.
There's a constant.
Yes, right, exactly. So first thing is actually A is directly proportional to x. In fact, if you want to be careful, you put a negative x. Yeah. And two, there is a constant of proportionality. Now this one I like to further break it down into two parts. The acceleration is directly proportional to x, and the direction of acceleration is always directed to fixed point. Now what do I mean by fixed point? It is actually the equilibrium position. For this one, it is here. For this one, it is here. So these are the two properties of anything that goes through. If you apply this to anything that oscillates with small amplitude, you'll find that it always obeys this form, which is A equals to minus, let's call it the alpha, the constant x. And the alpha depends on the system you're talking about. If it is a spring system, it depends on how big your spring constant is, it depends on how big your mass is. If it is a pendulum, it only depends on the length in your gravitational field strength. Still okay? Still alive? So copy this, even though it's not, even though you're going to have your notes for SHM, but it will not go through this specific examples and then inferring the general case. I think it's always good for you to follow through this thinking process. Then I'm going to show you what this constant is. Okay? And that will be another struggle over there. Can someone tell me what's the shape of a sine graph? Or probably before I go to that, any questions regarding this first? You have any questions? Scan once, scan twice. Okay, I see a lot of different kinds of eyes. I see eyes of apprehension, I see eyes of enlightenment, I see eyes of like nothingness. I don't know how to interpret that, but I will assume that if you don't verbalize the question, as of now, just still trying to feel around. So let's KIV this first. The idea that I want to send across using for this whole thing over here, there's only one idea. This one. Okay? And you need to know how to unpack it into two things. This one and this one. Okay? So that's the only thing I need to know. Now the next thing we're going to do clarity to this constant over here. What does this constant mean? So for that, I'd like you to focus on this thing first over here. Now take a look at this. Can someone tell me what's the shape of a sine graph? Yes. And what's the value over here? If it is theta, or let's talk about radians. 2 pi. But is it very useful for us to talk about oscillation? If you want to actually map out the position of a particle across time, is it very useful to talk about angle? Not that useful, right? I mean, we are more interested in the behavior of x across time. So the question is, how do we map this graph into a graph that looks like this? XT graph. Because anything that oscillates should have this kind of behavior. Yeah? Or a cosine graph. The question is, how should we change this equation so that it has a period of t in the time axis? Now this is where we do a little bit of math. Now if 2 pi corresponds to 1 period and an arbitrary angle corresponds to an arbitrary time, do a linear cross multiplication, the theta will be equals to 2 pi upon t. So this is something like the scaling. If you substitute this thing into here, which is equals to sine omega 2 pi upon t times t, you're going to basically convert the graph. All you did is to convert the graph from a theta axis to a time axis from 2 pi to t. So this jump from here to here is more mathematical to scale the graph so that it becomes a time axis.
So just to clarify, x is the probability distance.
X is the displacement from the equilibrium position.
Oh,
For this case, it will be this one. For this case, it is this one. Just as a side point, as you can see, the force is actually directed here, but the displacement is here. So it is only true for small displacement. Any questions as of now? Any issues? The idea about mapping a sine graph and any oscillation to this form. Give us 30 seconds. Figure.
Just to confirm, x bracket t is like x over t.
X bracket t. Oh no. X is a function of time. Yeah, like fx. F as a function of time. Yeah.
So for this diagram,
This diagram.
what is this two force?
Oh, okay. This force over here means this force and this force.
Yes.
What I did, basically what I did is to find the effect of mg. What's the component of mg that is the component that is responsible for pulling this thing back? So I broke this force down into this force and this force. So this is the one that's responsible for the storm.
And actually, you can
But
see
what is
what
it?
the
Sorry?
But what is it?
There are two ways you can resolve it. You can resolve it this way, and because there are rules that we need to follow for resolving it. First rule is that this must actually be hypotenuse. Second rule, it must be perpendicular. So once you draw this, the only way you can go is this way, not this way. Yeah. So it's the negative sign appears because we want to account for the idea that x is a displacement. displacement is measured this way, so the restoring force is opposite to the x. And you may actually see that, hey, come on, this is x, but this is actually the restoring force is in this direction. If you spot that, it's good, because you're correct. This is actually approximation. We're talking only about a very small angle. So for very small angle, like this, if you talk about resolving, it's almost horizontal. So that's why, remember your oscillation experiment, your teachers always ask you to have small approximation, small angle. Never swing it big. But actually, if you're interested, you can find out in your IAs in the future, what's the deviation from the equation at bigger angles? How much deviation? Is it a linear deviation or is it an exponential deviation? Find out. Okay. Let's come back to this. Come. Everyone okay with this? Because we need this form to show you something. In case you don't remember, can you still use, what's the name given to this?
Omega.
X. So it's omega t. Yeah, it's omega t. Okay? Angular velocity or angular frequency. Okay, so there are two things up to now. First thing, the general form. Second thing, this one. Now we're going to do the third thing. We're going to link these two up and give us understanding about what this means, what this thing really means. Ready? Yeah? Let's go. Okay, now we're going to do a little bit of differentiation. Differentiation is easy, no? X naught sine omega t. By the way, the sine omega t is sine omega t together, the omega t is together. It's not sine omega times t. Some people think that sine omega times t. So if I do dx dt, do you agree that it will be omega cos? If I differentiate again, d2, and this is b, d2x dt squared, do you agree that it's a?
Negative.
Therefore, it will be negative x naught omega squared sine omega t. Now, what is x naught sine omega t? X, exactly. So it's minus omega squared x. Can you see that if you compare it with, you can deduce that actually that is to say, the angular frequency for a spring system is actually square root k upon n. That is to say, the period of a spring mass system is this.
Wait, isn't that just the equation of the old ones that are not period?
Yes.
Root.
Yep.
Then,
But now what you learn is why is it that form. And now with the technique, you can actually, I can show you that you can actually divide the period for a lot of other oscillating systems. I'll show you later. So omega for the pendulum system is equal to this. Therefore, this is equal to 2 times square root L upon G, which I'm sure you've seen it before. What I did is simply take this equals to omega squared, and then equate omega to 2 pi upon T, and then find the expression.
What's the significance of x0?
The x is displacement.
The coefficient. X equals
X
to
naught.
x0.
Oh, this is the amplitude. Because the maximum value of sine is 1. Yeah, so you multiply x naught for x. So there are 3 learning points up to now. First learning point, the form of the equation of anything oscillating. Second, this is the solution. Third, which is that omega is equal to the square root of this constant. 3 things. Still here? Yeah, still here. Okay, good. Now I'm going to show you something else. I'm going to broaden your understanding of the solution to this equation. This is actually the general form of SHM. Anything that behaves and follows this is undergoing SHM. I use sine as a beginning. Do you think that this equation will arrive at this form if I use cosine? If I use x equals to x naught cosine omega t, will it arrive at the same thing?
Yeah.
Let's try. dx dt.
You get a negative example.
it should, then d2x dt squared, which is actually equals to a, is minus x log omega squared cos omega t, which is also minus omega squared. So either sine or cosine. In fact, I can use x equals to x naught sine omega t plus phi, an arbitrary phi. It also follows. Yeah, I just add 30 degrees to 29 degrees. It still follows. If you follow through the things, you will still get this. So that's the reason why. That's the reason why. Some students ask, why is it that we don't use x equals to x naught sine omega t to define simple harmonic motion? The answer is because you can use cosine, you can use anything in between to define. It follows an oscillatory function. Whereas, if we say that anything that behave and follow this will be SGM, you actually include all kinds of oscillatory behavior, whether it's sine, cosine, or anything in between. So that's why this is a very powerful, simple summary of what defines SGM. Okay? And this is what you should say when you're asked to define SHM.
Wait, what do you say?
Okay, I'm going to put it down in words. Yeah, but the equation is this. Cool. So a few things up till now. You need to know that this is form. I've repeated this a lot, but you need to know the form. You need to know that this omega square is actually the constant over here. Okay. And you need to know that this is the defining equation for SHM. Now what I'm going to do now is to show you the different kinds of questions you can ask. Okay. In order of difficulty. First level, define SHM. Seriously, this is the lowest level because you mark. Yeah? SHM is a oscillatory motion where first acceleration is directly proportional to displacement from equilibrium position, and the acceleration always point to the equilibrium position.
Do we need to mention the small analog displacement?
No, only.
And
Because if it doesn't obey that, then it's no longer called simple harmonic motion.
okay, and what's SHM? I mean,
Simple harmonic motion.
oh,
Okay, so level 1, the simple one. Level 2. This is level 1. Seriously, so this is the level 3. Please.
level one.
No, that's level 1.
What level is this?
This, we come to level 1.
Level two to what?
This is level 2.
Displacement from equilibrium.
Okay, if you were to draw a graph of A versus X, what would the shape of the graph be? A versus X.
Linear.
Yeah.
Linear like this?
No, it's a negative.
Yes, correct. So it should always look like this.
So it's counterintuitive, but
Yep. What about?
because when x is 0, by right, the A should be proportional.
Given this graph and these values, can you find for me the frequency of the motion? Level 2.
Oh,
If given the graph and given the values, can you find for me the frequency of the motion? Level 2.
period.
Wait a minute.
Period is pi, so frequency is just period is pi. I mean, stop. Period is pi. That was frequency. I forgot the equation.
Frequency is just
The period divided.
omega.
Oh, the total length is what?
Total length.
No.
Length.
No, period.
Where is
I
the
know
length
period.
coming from?
I know period. By right, I know frequency already. Right? I know period. I forgot how to
1 over
cover.
t equals 1 over t equals the frequency. Yeah.
Oh, so 1 over pi?
No, 1 over t.
1 over t. No, I mean the answer.
Oh,
thanks.
Okay. Work it out.
Because period is pi.
Do you realize that this is in millimeters?
Okay.
Do you realize that? Yeah.
Oh,
It always catches students.
what?
It's not a nice number. Sorry. It's square root of 1000.
Yeah, square root of 1000. Then it's going to mess up. Yeah,
It's not a nice number.
it's going to mess up. It's
It would be nicer if I give you centimeters.
yeah, centimeter would be much better. Then it's 10.
So,
So,
therefore,
so it's
omega square is actually equal to 16 over 0.04.
yeah.
Yeah. And then square root of this will be equal to 4000.
So it's actually 20 root 10.
And therefore,
Which means
period
it's an acme number.
so which
This
is
is 20, 10 root 10 over 9.
I think it's more 10 because root 10 is more 3.1.
I hate the
It's more 10.
I hate the very here. It's not nice.
Frequency is not 10. Okay, ready for level 3?
How do you use the equation? I'm so confused.
Now the equation is basically A equals to minus
So we
omega
are
square
already
x.
on level G, so
Also,
Ah. Level 3. Wow, wow. Okay, basically I'm using this equation over here. And up to now it's only about the equation. Okay?
wait, so but x is considered negative, right?
X is
So
depends. If you take A to be positive, say for example you take this, then X is negative. If you take A to be negative, then A will be positive. So eventually omega square must be positive. Otherwise you get a complex. You get a very complex number. Yes. So you have started complex number already. Excellent. Excellent. E to the power I theta.
E to the power
Uh-huh.
I
Have you done it?
No,
Okay, you haven't.
no.
Become
We only touch
Is it
I itself.
negative? So I thought it's e to the power of I 1 minus e to the power of I 1 plus.
I
Can
thought
be e to the
that's
power
some
I x though.
physics
So
thing.
either
It's just cos x plus I sin x. Yeah. Okay.
So,
Mhm.
for level 2, the x is displacement or distance.
Displacement.
Displacement for the equilibrium position.
But is this directly proportional?
Yes, directly.
Or even it's negative gradient is directly proportional?
Why can't negative gradient be directly proportional?
I mean, it's not proportional, is it great?
But,
Okay, I'm just very
Yeah,
confused.
it is directly proportional.
Okay.
So long as the straight line is directly proportional.
but it's true. Actually, when the displacement angle is small enough, the distance and displacement should be quite close, right?
Yeah, but
Right.
Okay, this question I'm going to state which direction is the positive displacement force, and therefore find the mass of the object. Find the frequency of the This requires more deduction.
It's mass.
Okay, let me explain what this graph means. Listen carefully. Listen carefully. Otherwise you're going to like this. Now, this is a system where the mass is hanging on the spring. Listen, otherwise you're going to be lost. Listen to this, you have time to discuss later. So I got the force over here acting upwards and the mass hanging on the thing. The spring is holding the mass there. I can move this down, I can move this up, that's what the displacement means. So at x equals to 0, it means that it is at the center. Equilibrium. Okay? So the forces, the object oscillates with amplitude 6 centimeters, I hope it's obvious to you. So the forces are given 40 newtons, 28 newtons, at the maximum and at the two maximum positions. So the question over here is state which direction of displacement is a positive displacement. Second, find the mass of the object. Third, find the frequency of the oscillation.
Wait, sir. It's upwards.
Upwards. Why? Because if you go up, your tension should reduce. Therefore, it should be upwards.
Actually, no need, sir, because F is upwards, right? When you see equilibrium,
Yeah.
it's the
You
y
You can see that
intercept
as
is
well.
above 0, so it's positive.
You can see that as well.
You just
Can because one of the way to do this is The reason why tangent decreases as you have a positive x is it must have gone up so that your extension is less. Okay. Now then, what is the mass of the object?
Find the y-intercept. Okay.
Okay.
What are the 2 points? 26,
40
28.
and 28.
Ah.
How do you find the mass?
You just find the description of the line, then y-intercept, then divide.
Fine. Then fine. Count. I love this question. Simple but do you agree that the value over here must be equal to the weight?
Yeah.
So what's the value over there? What's the midpoint between 40 and
34.
34 is correct. So what do you do with 34? Is the mass 34 Newton?
No, divided by
You divide by
3.47.
3.47. Now how do you find the acceleration? How do you find the frequency? Knowing that the gradient, but you have to be very careful. This is force. Is this net force?
net force. No.
Is it net force?
No, no.
Yeah. So how do you find net force?
Minus the v.
How do you find acceleration? You go ahead and find it. Because eventually you have to use this equation A equals to negative omega squared x to find omega. Then once you can find omega, you'll be able to find the frequency.
Sir, the oscillation is between up 6, down 6, right?
Yes, correct.
I mean, this is the whole. And we want what? Period?
Frequency.
Frequency. Same. The period of frequency is the same.
Not the same. They're related. But
With one step and one.
you get 1 mark minus away if you don't finish it. So, I'm sure that it doesn't hit the wall. It's much more complicated if it hits the wall. It's oscillating between 2 points. 6 centimeters and 6 centimeters below.
Okay, the force act downwards.
It doesn't act downwards. The force is always positive, it's always outwards. But the net force can be downwards. Consider this point. What is the net force acting on an object?
40 minus g.
So the acceleration is equal to 6 Newton, which is net force, divided by 3.47. So once you have the acceleration, you have the displacement from the equilibrium.
Which is 6.
6 centimeters. 6 centimeters. So what's x? 6?
0.06.
Yes.
And this thing,
Anyone with an answer?
W equals to R pi over T.
W equals to?
R pi over T.
R pi over T? No. W omega equals to 2 pi upon T.
Oh,
Or 2 pi f. Anyone got a frequency that would like to shout out? Follow. Which part? Must say no. Which part do you not follow? Raise your hand. Repeat again. It will snowball. Because whatever we're going to learn today, it will be the fundamental of whatever that's to come. So if you don't know, ask. You must ask. Which part do you not know? If you got to complain, what am I not sure?
1.17?
Yes, what?
1.17.
1.17. I didn't do the calculation. Can I just do a quick one? So it's 6 divided by 3.47 divided by 0.06 squared. And then
Then use 2 pi to
square root.
Yeah, then use 2 pi to divide it.
3.49. So which part do you want? say anything, think through which part will you lose, which part will you lose connection, which part do you understand up to. And that will give you hint as to where was the last part when you were still in the class. Yes.
So I just have right.
Yep,
I
go ahead.
have right. So is it just 6 newtons?
Yes.
You find the
The acceleration, that's right.
then you plug -6 and acceleration into that.
Into the A equals to minus omega squared. Yes, correct.
And
Then you find omega, once you find omega, equate it to pi f. I got 3.49. Very similar to the max value. Shall we agree? Which part were you lost? Which part are you? Which part do you understand up to? Then you look through which part do you still understand up to, do you follow up to? And that will give you a view of where you were lost. Must verify everything, must verify everything. Yeah,
I got the same answer, but it's wrong.
okay. Anyone got my answer? I could be wrong because I just did some quick crunching.
你算1、2、1、7 from.
Anyone got my answer or got another answer?
Yeah.
Don't be shy.
But the gradient is
Okay, my working is 6. How do I get 6? I got 14 minus 34. That's the net force. Divided by 3.47, that will be my omega squared, which is equals to 4 pi squared f squared. So f squared is equals to 6 divided by 3.47, and then x squared. Sorry, my x squared. I forgot my x squared. My x. Oh, now I know.
0.06.
I realize where I made my mistake. So this is 0.06 and then 4 pi squared. Then you square it over here.
4 pi squared. I think I'm wrong also.
6 divided by 3.47.
0.06 4 pi squared.
I don't know.
Now I got 0.854.
Yeah, so it's parts.
0.854.
Wait, sorry, where does that frequency square come
854.
from?
Sorry?
Where does that frequency square come from?
Omega equals to 2 pi f. You square everything.
So can you find gradient then
Oh.
use f equals kx?
You can find gradient, use f equals k. Then how do you find the frequency?
K equals omega, negative omega.
You can. You should find the same answer. You should. My answer is now 0.854. I realized that I squared the amplitude, which I shouldn't have squared it. Over by 3 minutes already.
So what is the answer again?
Again,
What's the answer again? Is it
0.854. 0.854. Right, people, unfortunately our lesson is over by already 4 minutes, so I will just pause this.
already?
It's only a 40 minutes lesson, a very quick one.